Okay, this is chapter 6.2, the second lecture for chapter 6. This one's going to get a little deep. We're going to talk about central limit theorem and determining the probability for a given sample mean. These are the two things you should be able to do after the end of this lecture, after some practice, and don't forget, after reading the textbook. Alright, sampling distribution is the set in our case is going in our situation is going to be the set of all possible means uh, for a sample statistic given for a given n. So if we have a sampling distribution of the mean, it's going to represent all possible values for the mean, right, for a given n. So this chart's showing a population over here. Oh, what happened? There we go. Sorry about that. Over here, this is a set of raw scores, a population of scores. From this, we draw infinitely many samples of size n. N is fixed. So if you think of every possible sample that comes out of this population of size n, we get the mean for each one of these samples, and then we create a new distribution. Right? Here's a sampling distribution of the mean. Sampling distribution, right? Sampling. Sampling means getting samples. So this is the distribution of the means that come from all of those samples. Now n, right, n is an important part of any sample. It defines the sample. So sampling distributions are kind of set or fixed to a particular value of n. Now the mean and the standard deviation, the statistics, depend upon the makeup of the sample. If there's a lot of variability, if the mean is different, but it's the characteristics of the sample that make up the sample means. But what this says is that most sample means will be alike. Few sample means will be towards the tails. But essentially, sampling distribution, we're referring to sampling distribution of the mean. Now, we could find the sampling distribution of the mean by doing what I just kind of said. We get a population, right? Suppose our population is just our class, 30 students. That's the population. If I were to randomly sample exam scores for 3 people, we'll make n equal 3. Right? I sample 3 scores from the population on the last exam, get the average of that sample, the x bar for that sample, right, and record it. And I do that again and again and again, each time getting a new sample. Think, how many samples of size 3 can I get from a population with 30 students? Right? How many unique combinations of 3? Right? That's an awful lot of samples. So you could do this, and mathematicians over the years have done this. They create a population and they get all possible samples because they know what the population values are. They get all possible samples, calculate the mean of each sample, and then create a new set. Right? This new set is a set of means, a set of x bars. That takes an awful long time to do, and who's got all the time? What's the mean, mate? Nobody got time for that. So the central limit theorem is a way to coming up with the sampling distribution of the mean without doing the actual work. I like that. I'm lazy. The central limit theorem gives us the characteristics, tells us how to find the characteristics of the sampling distribution of the mean. And it does that based upon the work of mathematicians. Mathematicians who have actually done the work have determined that sampling distribution of the mean, right, is related to the population. It's systematically related to the population from which the samples are drawn. And it is a lot easier than obtaining all possible sample means. This is going to be an important thing for us going forward, the central limit theorem. We're getting into hypothesis testing. And hypothesis testing means asking questions about sample means. And in order to answer the question about a sample mean, we need to think about all possible sample means. Here's an example, right? Imagine I reach into a bag. I got a bag of marbles. I reach into the bag and I know that there's red marbles and blue marbles and green marbles in that bag. I reach into that bag of marbles and pull out a red marble, right? What's the probability of me pulling out a red marble from that bag? At this point, it can't be determined because I need more information. In order to answer that question, I need to know about all of the marbles in the bag. I need to know how many total there are, as well as how many are red, how many are yellow, how many are blue. Right? You need to know everything there is about that bag of marbles. The analogy to what we're doing here is the sampling distribution of the mean is the knowledge about the bag of marbles. How many are there, what they look like, how they're distributed. The marble I would pull out is our individual mean. So for example, I might ask in the first exam, the mean, if I recall, was an 86. I might say, what's the probability of a class getting a mean of 86 on this exam? Well, in order to know that, I would need to know about the means of all classes that have taken that exam. I need to know the sampling distribution of the mean. I would need to know how many classes have taken the exam and what the result of each exam was. Right? I need that background information. The central limit theorem, it is a shortcut to give us the information we need in order to answer questions like that about the likelihood of a given sample mean. Now, in order to do this, in order to know the central limit theorem, there's some preconditions. In order to use the central limit theorem, we need to know mu and sigma. Right? Mu, remember, is the population mean. Sigma is the population standard deviation of the raw score population. Right? We need to know everything there is, the parameters of the raw score population. And of course, we also need to know size n. Alright, if we know those things, right, we can use the central limit theorem to tell us what the sampling distribution of the mean is. Now, the central limit theorem tells us three things about the sampling distribution of the mean. The first is about the shape. The central limit theorem says that the sampling distribution of the mean approaches a normal distribution as n increases to infinity. Right? This first bit right here is important. It approaches a normal distribution as n increases to infinity. What does that mean in English? Right? What that means is that it is essentially, the sampling distribution of the mean is essentially normally distributed. Right? Approaches, it says it's normal like, and it gets closer to a true normal distribution as n increases. The larger the n, the better the fit to a true normal distribution. Now, for me as a psychologist, what that means is that gives me the grounds for pretending, remember assuming, pretending that what we're working with is indeed normally distributed. If it's normally distributed, we can use the standard normal table, because we're using a standard normal curve that we talked about earlier in this chapter. Now, the technical part of this part of the central limit theorem is down here. Though, right, if n is less than 30, we can consider it to be normal. Right? I'm sorry, I got it backwards. If n is greater than 30, right, we essentially say, yep, it's a normal distribution. Once you get to 30, the differences between the sampling distribution of the mean and the actual normal curve are so small as to not matter. Right? It's good enough. If n is less than 30, though, it's normal only if the raw score population is also normal. So whether n is below 30 or above 30 matters for statisticians. It matters for statisticians. If n is greater than 30, there's no problem. They have no problem with using the standard normal curve. If n is less than 30, they say, well, we should only use the standard normal curve and assume it's true if the raw score population is also normal. In practice, for us as psychologists, I just roll with it. If no matter what n is, I look at the top part. Its approaches a normal distribution as n increases to infinity. That tells me it's okay to pretend that it's a normal distribution, no matter what n is. But technically, you've got to mention that bit about n of 30. All right, the central limit theorem also tells us about the mean of the sampling distribution of the mean. Because remember, what we're doing, right, is we're getting all possible samples of raw scores, right, and thinking about the means of those samples, which make up another set. The mean of that set of means, right, is we're going to call it the mean of the means. Central limit theorem tells me the mean of the means is the same as the mean of the raw score population. So down here, there's the symbol. This is the mean of the means, mu sub x bar, right? The mean of the means. Mu is a population mean, and we are talking about a population because we're talking about, right, the set of all possible sample means for a given n. All possible is a population. So mu sub x bar down here equals mu. So if we know mu, we know the mean of the raw score population, we also therefore know the mean of the means, mu sub x bar. And look at that, that's missing its little x bar right there. I'm going to draw it in. All right, that's easy. The mean of the mean is the mean of the means. The third thing the central limit theorem tells us is the standard error. Standard error is the standard deviation of the set of means. We call it standard error just to give it a different name. Right? You don't want to have a lot of people with the same name in your family. It gets confusing. So we call this the standard error. The standard error of the sampling distribution of the mean is related to the standard deviation of the raw scores. So, right, the symbol for this, the standard error is right here, sigma sub x bar, sigma sub x bar. Sigma is a standard deviation, x bar tells me what it belongs to. It's the set of all possible sample means. Here's the formula, here's how they're related. Sigma sub x bar equals sigma over the square root of n. Right? This is the central limit theorem. The central limit theorem tells me everything I need to know about this population of sample means for a given n. It tells me it's normally distributed, tells me what the mean is, it tells me how to find the standard deviation. It looks like an unhappy face. Don't be unhappy. Right? Central limit theorem tells me those three things about the sampling distribution of the mean. That's important, right? It's going to be useful for us down the road. It tells us the shape, and we've been through the standard normal table. If we assume or know that it's normally distributed, we know an awful lot about the areas under the curve, right? We know the boundaries for, say, where's the 50% point, where's the 75% point, where's the 20% point. Knowing how to find mu sub x bar and sigma sub x bar give me the values to scale that distribution on the x-axis. So here's some examples. There will be additional examples in Stats Garage. You'll see why it gets a little bit awkward. So if this is the raw scores, here's a set of raw scores, a set of x's. All right, let's say represents an IQ test. All right. IQ tests typically are distributed so that the population mean of individuals is 100 and the standard deviation is 16. This is typical. So, right, here's the center, right? This would be 100, right? And then the standard deviation, right? Here's a standard deviation. This is minus 16. Or you do 100. I can't draw that. It's not going to work. Right? There's minus 100 minus 16. That would be what? 84. And this would be 1, 1, there it is, 116. Yikes. Right, tells me how to scale that population. Now, since it's normally distributed, right, 50% of people score less than 100, right, 34.1% are between 100 and 116, right, this slice right here, right, think back to all we know about a normal curve. The central limit theorem, if we apply the central limit theorem, right? For n of 36, what do we get? Well, we get a new distribution, right? We got all possible sample means. So imagine all possible groups of 36 coming from this population. Each individual set of 36 people is a new sample. We get all those samples, right? Get their means and collect them over here. Here's the distribution of sample means, right? Here it is, the distribution of means that we've sampled, right? Well, mu sub x bar is going to be 100. And here's where these slides don't work out so well because the top hat slide, I had the notation printed. I couldn't figure out how to do mu sub x bar over here. So bear with me, right? Mu sub x bar equals mu, right? So if we know mu from the raw scores, we know the mu of the sampling distribution. Here's sigma sub x bar here. Central limit theorem tells me that sigma sub x bar is sigma 16, right? 16 divided by the square root of 36. The mathematical notation was real hard to type, so I just wrote it out like this. The square root of 36 is my math is way wrong here. It's 6. Square root of 36 is 6. 16 divided by 6 isn't 4. Hang on a second. Right, the square root of 36 is 6. 16 divided by 6 is, oh, there it is, 2.67. See, even on these slides, there's still mistakes. That's not PowerPoint. Sorry, that's not top hat. That's all me right there. Anyway, let's back up. Sigma sub x bar, right, from the central limit theorem is sigma 16 divided by the square root of n, which is 36. 16 divided by 6 is 2.67. So the set of all possible means has a mean of 100, right? Here's 100. And the distance to each standard deviation is 2.67 IQ points. Notice how the distribution of sample means is narrower. There's less variability, right? The standard error is 2.67 versus 16, right? There's less variability with sample means than with individuals, right? Sample means tend to vary less than individuals. So we know the mean, we know the standard error. The other thing the sampling distribution of the mean tells me is that this is normally distributed. N is over 30, so I know that this is good enough, right? That the shape of this distribution is indeed a normal curve. So the set of all possible means for n of 36 has a mean of 100 and a standard error of 2.67. Here's another example, and I'm pretty sure my math is good on this one. So once again, right, here's all the individuals, right, set of population of individuals. Let's say this is an exam score in statistics, first exam in statistics. Population mean is 75.6, standard deviation 14.9, and we'll say for n of 30. Right, so we know everything there is about the base population of raw scores. Here's the sampling distribution of the mean. I'll label them x bars. Right, central limit theorem tells me mu gives us mu sub x bar. There it is. Mu equals mu. 75.6 is the mean of the means. The standard error of the mean, sigma sub x bar, is the standard deviation, 14.9, divided by the square root of 30. I'm just going to assume that number is right from the other day. 14.9 divided by the square root of 30 is 2.71. It sounds about right. So there's the center value, and the standard error is that distance right there, 2.71 points. The other thing, remember, the central limit theorem tells us, again, is that this curve is a normal distribution. And checking n is 30, I'm good with it. Now think, why do we need to know about the sampling distribution of the mean? We'll go back to where I started, right? It tells us how we can think about sample means. And before we go forward, right? So the set of all possible means for n of 30 has a mean of 75.6 and a standard error of 2.71. Right, here's how we use the central limit theorem. Once we know the central limit theorem, we can find the sampling distribution of the mean, gives us the mean and standard error, and then we can use that to find z-scores that match a given sample mean. At the beginning of this chapter, we talk about finding z-scores for individuals, x's. Well, now we can take that to a higher level. We can think about the z-scores that correspond to a sample mean. So how do we do that? First, right, we use the central limit theorem to determine mu sub x bar and sigma sub x bar. Now, what does that presume? That presumes we know mu and sigma. Remember, you got to know mu and sigma from the raw score population, and then we also have to know what n is. Right? Then we use the central limit theorem, as on the previous two slides, to find these values. Then we put them into the z-score formula. X minus a mean, score minus a mean, divided by standard error. So we convert the sample mean into a z-score. Once we have a z-score, we can use that standard normal table, this is why we reviewed it, to determine the proportion below a given z-score. So go back and look, right? Go back and look. Here what we got here. X bar, sample mean minus the mean of the means, and divided by the standard error, sigma sub x bar. Remember, it's the central limit theorem that's telling us there, like this, right? Telling me what that is and telling me what that is. Where do these numbers come from? Right? They come from knowing the raw score and knowing what the central limit theorem is and what it can do for us. So here's an example. I'm pretty sure, nope, this example is going to be a little, yeah, this example isn't any good anymore because this is the one I messed up on. What I'm going to do is take a pause here, but these are going to be, I'm going to do a couple of these on the Stats Garage and post them separately so you can see them. Alright, there will be some on Stats Garage, but here is one I worked out real quick. I think you can see it. And it kind of goes back, it goes back to the prior example that I said was from a statistics exam. And let me start the slideshow. There we go. So from a statistics exam, suppose I know for all my classes the mean, the mean of all possible, the population mean is 75.6, and with a standard deviation of 14.9. There we go. Right, so n equals 30. The central limit theorem tells me that the mean of the mean is 75.6 and that the standard error of the mean is, and here's the math that was on the other slide, 2.71. So then here's where this new bit comes in, right here. Is an exam mean of 86, now this is about the mean you all got on the first exam, is that a common or uncommon occurrence? Well, in order to know that, I need to know about all possible sample means. So this 86 comes from this distribution that has a mean of 75.6 and a standard error of 2.71. Right? So to figure out where this score is relative to all other scores, we convert it from an x bar from its mean to a z-score. Here's the z-score calculation. That is x bar minus mu sub x bar over sigma sub x bar. Sample mean minus the mean of the means divided by the standard error of the means. 86 minus 75.6 is 2.7, divided by 2.71. 10.4 divided by 2.71 is a z-score of positive 3.83. So you see here I did a sketch to kind of see where it is, right? Where is this z-score in a normal distribution? Well, there's the center of a 0, and I put in some standard deviations. 3.83 is way out here, right? So is this a common score or an uncommon score? I'd say it's an uncommon score. Look at the frequency. The curve here is very low, right? It's way up at the top. There's a lot of people. Most of the distribution is below it, right? From 3.3 all the way down here, right? It has a low frequency. So just knowing it's normally distributed and seeing where that z-score is on a chart lets me understand the performance of the sample. But this is the eyeball test, and it's a bad eyeball test because I just sketched this in here. To be precise, I've got to look up a a z of 3.83 in the table. When you do this, you see that is such a high value for z that it's not even in the table. There's a note. Oh, come back, come back, come back. Sorry, hit the mouse. Oh, I keep it. Come back. Sorry, this is the last slide. And all right, there we go. It's the table only goes up to 3.49. So there's a note that if z is greater than 3.50, use 0.9998. So that's what we use. So here, 99.98% score less than this mean. That tells me without a doubt that this is indeed an uncommon mean. Sorry about that mess up with the slides back and forth. I'm going to leave all this here. I'll save it. I'm also said, as I said, I'm going to post some Stat Garage videos that are just this. So what you should do is make sure you can use that table. We're going to be looking up some probabilities and right being ready to think, right, not only what does the z-score tell us, but what does that area to the left tell us about that particular mean.